e ele mudou o título dessa conferência. Ele vai falar hoje de geometrization of low-dimensional manifolds. Quero ajudar, que é a primeira vez que ele vem no Brasil, ele gosta muito, ele me falou que ele vai voltar.
Thank you for introduction, though I didn't understand much. And so anyway, so it's a great pleasure to be here, and as Harold said, it's after spending 3 weeks here already, and it's a nice place to be here, and I like it, and it's a pleasure to give a talk here again. Okay, so I change title a little bit. Its title is slightly different from the one printed in the bullet, and it's probably that some the last 3 weeks I also give a course on the Poincare conjectures. So today I will emphasize more on geometrization, and this is a more appropriate title because in the end I will spend some time, not too much, on the 4-dimensional things, on the things I'm interested in doing. So this is a general talk, though I include a few formulas, but most times I just can very expository. Okay. So in this talk, I assume M is a compact manifold, and C is an open set in a Euclidean space, and to see a low dimensional basically means a dimension less equal to 4. So n in this talk basically is less equal to 4. So in geometry, what we study is we study geometry of matrix. So locally, a Riemannian matrix is given by matrix valued functions. So it's positive definite. So that's a G with it below, I guess. So it's a matrix valued functions. So it has been known for a long time. So the curvature is invariant, only invariant of a metric and diffeomorphisms. Namely, if you change your way of presenting these metrics, then this curvature will stay the same. So it also measures how space is curved. Space is curved. Okay. Then we start with a surface case, namely the case dimension is 2. So now the curvature is determined by Gauss curvature is basically given by one functions. So the most natural condition you can imagine, since a curvature is simply a one function, or locally simply anyway it's a function. So the most natural condition on metric is to make a Gauss curvature constant, make a function constant, because that's the simplest function, constant function. So in the last for many years we studied geometry. We want to find a good metric with a nice curvature condition, and then we can use this to study topology. So here is a few examples, basically what I'm going to do here. So giving since we want to make curvature to be a constant, I mean, of course, there are many metrics, just like you have many matrices and many matrix valued functions. So we need a way of doing that. So one natural way to do that in the 2 dimension is giving any metric, one can just try to change. I think this may be too close to this. So try to change a metric in such a way, so-called conformal change, so that the resulting metric has a constant Gauss curvature. But this is amount to solving following partial differential equations, and so here the G0 is G0 is a given metric, and the G is a metric you want to find out. You want to find, and it will have a constant Gauss curvature. So this is like we try to solve these partial differential equations. Lambda is simply a constant here. This equation has been studied a lot in the last, maybe last 30, 40 years, like by Nirenberg, Kastenweiler, and Obang, and so on. So the upshot is the outcome is you can solve this equation. You can always solve this equation, so that giving any so this way you get the following theorem. So giving any two manifold and a conformal class, so-called conformal class simply means you only change you have a group class of metrics which are just different by some scalars. Okay, so there is always a metric with constant Gauss curvature. That means the previous equation always solvable. So as a consequence of this, by using a classical theorem in the Riemannian geometry called the uniformization theorem, you can immediately say a universal covering of this space is one of the following type. Okay, so it's standard. So in fact, this theorem was also proved in the other ways, because if you in the complex analysis, you probably know there's a Riemann mapping theorem, which will give you the same conclusion here. But the difference here from other approaches is a priori, you don't need to know what the topology of a manifold is. So what you do, you're just giving a manifold surface and trying to find a good metric. As a result, you conclude the topology is known. You know the topology. So let's go to high dimensions. So in high dimension, what we want to study is so-called Einstein equation. So this involves a so-called Ricci curvature. So Einstein equation simply say a Ricci curvature is multiple of a metric. So Ricci curvature again locally is just metrics. It's just metrics. It measures the deviation of a volume form from a Euclidean one, because it's just part of a curvature. And it tells you because space is curved, you may have a different volume form, okay, at different points, because space is curved, and it's unlike Euclidean space. You somehow you can integrate at any point. It's basically it has certain invariance. But in a curved space, you have to it's maybe different. So in dimension 2, Einstein metric is simply a metric with constant Gauss curvature. So it's a natural extension to high dimensions. So here's some very brief illustration what a Ricci curvature is. So if you think you fix a point P, you can take this as definition. It can be made rigorously. So you look at the nearby points, and you look at suppose these nearby points are roughly given by these unit tangent directions. And then you look at the volume form of a metric at this point, and then compare with the volume form at this fixed point, that's the dv0. You can think that's a Euclidean volume form. So the because space is curved, so these two are different. So the deviation is given by Ricci curvature. It's the next term. So now we assume M is a compact three manifold. Just for simplicity, assume it's compact. And so if M admits the Einstein metric, that is, we can solve the previous equation for some constant, then its universal covering is of the form of this. Okay, so this is again is same as what we had before. It's also a result of so-called uniformization theorem. So this way, if you know, giving a three manifold, if you can construct solve the Einstein equation, and then you know the space is standard. Okay. So now the question is, does M admit the Einstein metric? Unlike in the two-dimensional case, in general the answer is no. So the substance geometrization conjecture basically says is any three manifold can be decomposed in the natural way into these Einstein three manifolds and plus some graph manifolds. So I have no intention to define what graph manifolds are now, but they are just the manifolds which were understood, whose topology was well understood, maybe at least 40 years, for 40 years. So Poincare conjecture is just the case that M is simply connected. So the paramount recent work is to solve this conjecture by using a Ricci flow, which I'm going to say a little bit, and in the next maybe half hour. Okay, so the Ricci curvature was introduced by Hamilton in the early 80s. So this provided a method of deforming a metric towards an Einstein metric. Okay, so it just deform in the direction of a Ricci curvature. So it's like a metric version of a heat equation. So you're giving a heat, giving an initial value, then you evolve along the heat equation, then the heat distribution become more homogeneous. Okay, so hopefully this Ricci flow also have can deform a metric towards a more homogeneous metric. So like Einstein metric. Okay, so this is a parabolic type equation. The local existence was established a long time ago, more than 25 years ago by Hamilton and the talk. So this short-time existence is always okay. You can always find a certain time, and the flow has a solution. The problem is how far you can evolve the metric, whether or not you can evolve the metric to eventually a nice metric. So here, so there is a so-called maximum solution GT of a Ricci flow on this. So from 0 to capital T. So this capital T is capital T is a time such that the solution of a previous equation exists. I mean, it cannot extend further. Okay. So for any any of this flow, you can have such a things. So then you have so-called this characterization of this maximum time. So either this is infinite, you can deform all the time, or this is the curvature has to blow up. So this was proved by using Shi's estimate on high order derivatives. Okay. So next thing was important in this Paramount's work towards on the geometrization conjecture is evolution of curvatures. So Hamilton established the following curvature equations on the evolution of curvatures. So you can think the curvature tensor as a matrix. So in 3 dimensions, just 3 by 3 matrix, symmetric matrix, and this is a square of matrix. This is in 3 dimensions simply given by this. It's just adjoin the matrix of giving matrix. So what is nice in the 3 dimensions is if we want to apply the maximum principle to these curvature evolution equations. So actually Hamilton proved there is a function phi. This function goes to 0 at nearly infinity, such that the curvature as a 3 by 3 matrix is always bigger to minus phi r times r. R is a scalar curvature, is a trace of this, okay, up to some constant. So r here is just simply a scalar curvature. So scalar curvature is simply a trace of a matrix here. So this theorem says if you think just play around a little bit the linear algebra, you can get the following conclusion. This says if you think you have a matrix which has a very, very large eigenvalue, okay, with very, very sufficiently large eigenvalue, then if we satisfy this inequality here, then you immediately find the trace has to be positive, and not only that, you can also see the largest positive eigenvalue against the largest negative eigenvalue. I mean, it's much larger than what I mean. Largest positive eigenvalue is much larger than than negative eigenvalues. Okay, so in this sense, is if you normalize the matrix by 1, like divide by chess, then the negative eigenvalue become very, very small, and the positive eigenvalue become like normalized, bounded. So in this sense, you can think this is condition basically says the space you are starting near the point where the curvature is very, very big is basically like non-negative curved. Okay, non-negative curve. So that's why we say it's pinched towards positive here. It's just a convention.
Rm is a matrix.
Pardon?
Rm is a matrix.
Rm is a metric. It's a curvature tensor. It's
R is a scalar.
R is a scalar, but there's identity here. Okay.
What do you mean by this inequality? Refer to the eigenvalues or
You can refer to yeah, it refer to eigenvalues.
the eigenvalues?
Yes.
Okay.
Okay. So if a rich flow has a global solution GT, and possibly after appropriate scaling, which converges to a smooth metric G infinity as t goes to infinity, then this G infinity is an instant metric, and so a universal covering is a standard, which which if you here I appeal to a result I stated before. So then you know what the topology is. Okay, so one successful example was due to a Hamilton more than 20 years ago. If an initial metric has a positive rich curvature, then the rich flow has a global solution, and after scaling has a global solution, and which converges to smoothly to metrical constant positive curvature. That means the space is just a finite quotient of a sphere. Okay, so it's like you prove. I mean, this condition. If you have this geometric condition, then the space is standard. So however, rich flow develops singularity at finite time, and singularity can be either forced by topology or caused by complexity in a metric behavior, even if a manifold has simple topology, even even topologically like S3, but the initial metric is very complicated, and in general we if we don't know what the topology of underlying space is, it's not possible to know precise what metric is. So this may happen, or even on a singular space. So latter singular can occur along proper subsets of manifolds, not on the entire manifold, because then this is more complicated case. Okay. So because of this, one is led to starting a more general evolution process called the rich flow with surgery, and this kind of it's like more like a generalized solution for rich flow, and the solution of this sort was first studied by Richard Hamilton in studying 4 manifolds with isotropic positive curvature with certain positivity on the curvature. So the evolution process is still parameterized by an interval in the time, so that for each time in the interval of the definition there is a compact 3 manifold. So, but 3 manifold may depend on t. So, but there is a discrete set of times at which manifolds and the matrix undergo a topological or metric changes, okay, surgeries. So, but in the so you have this discrete set of time which form a closed set. On the complement, it's just possibly countable many of open intervals. So in each interval here, the evolution is just usual rich flow. Okay, though the topological type of empty changes when t cross from one complement interval to next. Okay. So this definition is very general. That means this because it does not really tell you. It's how this manifold goes through a surgery. Okay. So to be useful, one needs to control both the topology or geometry of surgery process at singular times. So, for example, I give an example. It's crucial for topological applications that we do a surgery only along the tooth fields rather than on the surface of a high genus. Because surgery along the tooth field produces connect sum decompositions, which is well understood topologically, while surgery along the tori, which is only a surface of genus 1, is just genus high, just higher than genus of sphere by 1. But even that, the surgery along the tori can completely destroy the topology, changing any three manifold into any other. So if you cannot control the surgery surface, genus of surface, even you just increase by 1, you are hopeless in this program. Okay, so here is so in a groundbreaking work, the Perelman established the following things. So this is the key existence theorem for Perelman's proof of a geometrization conjecture by using a Ricci flow. So this says the following: if you have any three manifold, closed three manifold oriented, and if you have an initial metric, if there's then there is always a Ricci flow with surgery. With surgery defines this. Okay, the set of discontinuity times, that means that where you do a surgeries, is a discrete subset, and this discrete subset actually has no accumulation point in which I didn't specify here. But in fact, you can prove it has no accumulation point in this, but it may be infinite set. Okay, so the topological change, the key issue here, the topological change in the three manifold as one crosses the surgery time is the connect sum of decomposition together with a removal of connect components, each of which is diffeomorphic to either S2 cross S1 or RP3, connect sum with RP3, or a manifold of admitting a metrical constant positive curvature. But this is simply a finite quotient of standard fields. So all these things which you either removed during the surgery process or dropped are standard, are well understood. For example, if you assume the initial manifold is simply connected, and none of this is simply connected, so you can accept the last one is field. So you can basically drop. You don't have this at all. So namely, if you have you start with simply connected manifold, then each time you do a surgery, you may drop something, but the topology does not change. You only drop fields. You only drop balls. Okay, you only drop balls. So this gives you some idea how powerful this theorem is. Okay, so this is the key existence theorem. So basically, with this existence theorem, what you do is you want to apply this to a three manifold and analyze this limiting behavior of these things and see whether you can prove a geometrization conjecture. So now let me discuss briefly on the main ingredient in his proof. So how did the Perelman make sure you can only do a surgery along the tooth fields? Okay, along tooth fields. So the key things he did, which was actually I gave a very extensive discussion in my course prior to this colloquium, and you there must be a way of finding that. So anyway, so he introduced a new length functions for Ricci flow, and called the reducer length. And this he developed a theory for this length function, which is analogous to a theory of a Euler length function for in the Riemannian geometry. In the Riemannian geometry, you probably can find it in the standard textbook. Okay. So using a reduced volume, Perelman defined reduced volume. Reduced the length. This is a misprint here. Perelman defined a reduced volume, and the reduced volume is a long decreasing and associated backward redshift flow. So this is a fundamental tool Perelman used to establish non-collapsing results, which is a key to rule out surgery along the high genius curves. So this is the key monotonicity result. So also with the modifications and on the domain of integration, one can have a definition and analysis of reduced length and reduced volume as well, and its multiplicity in the context of rich fluid surgery. So this is actually the part if you want to really understand it, you have to probably read the papers and the book. Okay. So now let me state a little bit more precise what he proved as a corollary of his new length functions. So one thing is called non-collapsed, kappa non-collapsed. What do you mean non-collapsed? So that means that if you have a solution for rich flow, if a curvature are bounded by certain constant on the size of parabolic on size of this ball here, so then the volume has to be sufficiently big. So the roughly speaking says if a space is sufficiently curvature bounded, means a space is flat, okay, locally flat up to certain, or has a bounded variation from flat space. Then the volume cannot be too small. For example, if you have a cylinder, very very thin cylinder, that's collapsed. It's not let's say. So if you think torus is a flat, it might have a very very long. It can take a cylinder, very long cylinder, and glue them on both ends. That will give you a torus. Okay, and the torus is flat, and that is something we need to rule out. I said before. So this is, but then with this one low bound of volume, you cannot have that. So especially this as application of this estimate here, this looks very analytic. Then one can rule out so-called cigar soliton as a possible answers for singularities in the rich flow. So this was something which people want to exclude for a long time. It's a cigar solution is one particular solution for rich flow. For rich flow, it's a special solution, and it has a shape of a cigar with a very infinite end, and so it's two-dimensional things. But you can also cross with a circle to become a three-dimensional thing. But the infinity, because it's almost like a cylinder, so it's very flat, and it's okay. I just so it's very flat. So curvature is very small. Okay, and the cross section here is more like maybe I need to draw bigger, but anyway, so cross section is a torus. So for a long time, you want to exclude this as a possible singularity formation. Okay.
What is capital B?
B is a ball, stands for geodesic ball. So B stands for geodesic is a ball of at the center x, at the time t, because we are considered the family of and at the radius r. Okay.
Riemannian metric ball.
Riemannian metric ball, yes. Any further questions? Okay, so in particular, consequently, it suffices to a surgery along the two spheres. Okay. So another application there are many applications. I just list the two major things here. So another application is can classify so-called kappa solutions in dimension 3. a kappa solution of rich flow, here is a definition, is a solution of rich flow defined for all the time back to minus infinity. So it's Nipidus change here. I mean, let's finish this. So each time slice is a long flat and complete three-manifold non-negative unbounded curvature, and each time slice is a kappa long collapse for some fixed kappa. Okay. So now what's called it's kind of like ancient solution, because you can go all the time back to minus infinity, because I said the rich flow is parabolic equation. It's easy to you can evolve forward, but moving evolve backward is unusual. Okay. So this is very special type of equations. When we study probably people in PDE all know, when we study nonlinear equations, parabolic type of equations, when you encounter singularities, what do? You want to scale, blow up a singularity and find a solution. And that solution is most time just the so-called ancient solution. They exist for all the time to a minus infinity. And then hopefully you can, these solutions are very special. You can prove, you can classify them. For example, prove they're just solitons. And that's actually very special. In this case, in 2 dimensions you can do that, but not in 3 dimensions. So then hopefully then you say, okay, because singularity near the solution near the singularity is just approximated by solution of this type. Okay, so this is very important for classifying types of singularities. So using a reducer length, the Paramount classified topological all the kappa solution in dimension 3. Okay, dimension 3. So that's enable us to understand all the surgery types, and when you for solution for generalized rich flow. Okay. So another contribution of the major breakthrough, I think, of Paramount, in my opinion, is to prove the region of a big curvature is approximated by kappa solution. So this is roughly, this I already said something like that on the previous transparency. So on the previous page, so this also justifies why it's important to classify kappa solutions. So we say we know that before near the singularity, the curvature has to be sufficiently big. So now this result says that the region of big curvature is approximated by kappa solution. Okay, so this is fundamental in his approach towards geometrization conjecture or Poincare conjecture. So it particularly implies there is R0, which depends on an initial metric, is bounded away from 0 in any given time interval, finite time interval, such that all the points where the curvature big equal to this constant from below. So this always make it in a scale invariant way. Okay, have a canonical level hertz. So I have no intention to define what canonical level hertz are. It's involve a few inequalities, but in short, this is simply a level hertz which can be described in a topologically analytic controlled way. That's okay, controlled. So once we have this, we can do a surgery. So namely, if you suppose you already have a rich flow with surgery up to time t, so then what you do is you fixing some small time before the t, capital T, so that there are no further surgery in this time interval. So what you do then, by previous results, you know exactly how the flow looks like near the part where the curvature is very, very big, and that means near the capital T, and near the region where the curvature is sufficiently big. So then you can cut out the parts where the curvature is sufficiently big near the T, and glues in some standard caps, some standard solutions. Okay, So, and continue the flow. So you extend the flow across capital T. So this is very brief in describing a surgery, but the key points of the argument is basically following few properties, and this takes a lot of pages especially in the Paramount standard of details. Okay, so this is so one must show if there is a rich flow with surgery defined for some time. Suppose you satisfy these conditions. So one is a normalized initial condition, which is easy because you just need to do it at the beginning, and the curvature is pinched, and that's you can do that relatively easily. It's actually very easily because you just make sure your surgery process will keep this property. Okay, it's more like local computations. So next two are rather difficult to check. So all the points of a scalar curvature, all the points where the scalar curvature is sufficiently big have a canonical neighborhoods. That's what I said. So geometry and topology are in a controlled way. Or chi-pi-long collapse on all the scale, let's say equal to epsilon. So epsilon is just some fixed small constant so that there are certain geometry are stabilized. Okay, it's some universal constant. So then it's possible to extend the flow past the t, so that like what we did before, to larger time, keeping all these conditions satisfied. Possible with different constant, So this is the key part of argument and the very technical part of argument, and a major part of Paramount's second paper is devoted to proving these properties when the surgery parameter is chosen sufficiently small. I guess so. Namely, this delta I didn't write before. Delta is just size of a cap. You do when you do a surgery. So he also proved above R0 and the chi-pi. That means the constant appeared in these properties can be made uniform on any finite time. So this is at the beginning people wondered why, since you may have infinite many surgery time, how do I prove there are only finite many surgery time at any given time? So this is a key point, because the arguments, if you carefully went through arguments, in fact his proof sure this constant can be made uniform. Okay, so this follows your surgery time cannot accumulate finite time. So here maybe I stop to say a few words, because in a sense this Paramount's proof used many work in the geometry in the last 40 years or even longer, and this is a really good thing to know. So here I just give a few examples. So for example, he strongly used the structural manifolds way of a non-negligible curvature, so like a Soule theorem. So this was proved in the later 60s. For example, splitting theorem, that also proved in the later 60s. So and also, of course, when I say splitting theorem, also there's an extension of that to Ricci flow, and that also used. So, and the Harlock inequality for Ricci flow proved by Hamilton. So this is nonlinear extension of Harlock inequality for Hity equation by Lie type. So also the compactness theorem for matrix with bounded curvature. Of course, this compactness theorem was first studied by Jeff Chigger in his thesis, but then with many extensions, and so including extension to Ricci flow. So now, assuming this so now I finished roughly description of proof for this theorem here. So now with this theorem at hand, so we want to go ahead to prove geometrization conjecture all this Poincare conjecture. So to do that, with that key existence theorem, we need to analyze the asymptotic behavior of above Ricci flow with surgery. Okay, so this was done in section 6 and 7 in the second paper. He analyzed this asymptotic behavior. Okay. So more precisely, he proved one thing. So he proved quite a few things. So I give you a sample of these things needed. So you need a certain stronger version of these, but in the same spirit. Okay. So namely, for any W positive, R positive, and small c, there is a time depending on those constants, such that if a volume up to scaling here, so this factor is because you need to scale in a proper way. So big equal to, if a volume is sufficiently big for t0 sufficiently big, if a curvature is bounded from below by this, okay. So then again, forget t0 here. It's t is t0, okay. So t0 is just normalization here. So then you look at the Ricci curve. If you forget this constant here, this simply means the Ricci curvature close to a -1, okay, up to scaling. So because c can be made very small. So basically here you says if you have a low curvature bound up to scaling and have a volume, low bound of volume, then this part so this is measured on this ball. So then this part of a metric is very close to hyperbolic one, So he proved this by using some results from Alexandrov spaces. So which says for an industrial space of non-negative curvature, you always have a tangent cone, and if you adapt that into a Ricci flow, actually give you a further strong result. And also adapting some arguments by Hamilton, because Hamilton proved this kind of thing estimate before by assuming a curvature bounded. So it turns out that those arguments can be adapted into these more general cases. So then what you can do is you can define you can do a decomposition of a manifold, so-called a thin decomposition of a three manifold MT in the Ricci flow with surgery. So what you do is you introduce this radius here, which is largest radius such that the curvature is bounded from below by this, okay, on this corresponding ball, So it's largest R, radius R, such that the curvature bounded from below by this constant. So if you cannot find such R, for any R this is true, then you just take this to be infinity. Okay, so this is just definition. So you let M minus WT be a set of points in the MT. MT is the domain of a Ricci flow with surgery at the time t, such that the volume is small. Volume is bounded by this. Okay, so M plus is simply a complement. So this is just definition. Okay, it's a decomposition. You decompose the manifold into two parts, and the things you have to analyze each of that. So, but for one part, for this, if this part is non-empty, for any fixed W, if t is sufficiently large, so we can use this result here. We can use this result if t is sufficiently large, if W is fixed, and then this is sufficiently close to a portion of hyperbolic three manifolds. Okay, in fact, using a certain hyperbolic rigidity, one can show that for W sufficiently small and T sufficiently large, the M plus, if it's non-empty, is a finite union of a truncated hyperbolic three manifold. So when I say truncated hyperbolic three manifold, I simply means this is a complete finite volume hyperbolic manifold with the neighborhoods of cusp at infinity removed. So this may be draw. So if I have a complete hyperbolic three manifold with a finite volume, so because of finite volume, and the infinity is always a cusp. So here I draw the two cusps. So and near the infinity is the cross section is a tori. It's a tori. So near the infinity is always a T2 cross like interval. Cross interval. Okay. So when I say truncated, simply means you cut off certain this part. So without a really transient topology of manifold. Okay. And you cut this so that this size already become very, very small. Okay. So this so-called this thick part is topologically is very clear geometry topology. Then the adapting of argument of Hamilton, which actually involving use the result of mixed Yau on the minimum surfaces. The Perelman showed that the boundary of this consists of incompressible tori. So this tori here, which when you cut off, we already know these are tori's. So here you do also tori. And you need to prove these are incompressible, namely, so anyway, let me not go time it up. So you prove it's compressible, so the namely fundamental group injects. Okay. So more recently, the John Lott found a simpler proof of this incompressibility by a more direct elementary method. Okay. A kind of volume computations. So now this is what so far we understood well of. I guess it's to run a little bit fast. So if n minus this thin part, if it's empty, then we are done because just hyperbolic manifold. So if this is another exceptional case, if this whole manifold and for some x and the diameter, this radius we defined before is much larger than the diameter. So then one can show this MT is a flat manifold. So after this exceptional case are studied, then the geometrization conjecture is reduced to a result of collapsing three manifolds with curvature locally bounded from below. Okay. So here is a precise statement. Maybe I up to this now. So this is basically a copy of a statement in the paper. So this is so-called 7.4 in a Perelman second paper, and I just cut. I sometimes abbreviate a state condition in a rough way. Okay. So anyway, so let's see. So if you assume these things, then the geometrization conjecture is done because what left here. So this is what this thing. If you apply this to m minus wt for w sufficiently small and t sufficiently big, then that is a graph manifold. Then we are done. Okay, we are done. So basically, you say the manifold you start with after doing a few surgeries, which you drop by dropping a certain standard manifold, then you come to this thick and thin decomposition, and the thick part is a hyperbolic, and thick part boundary are given by compressible tori, and the thin part are graph manifolds. So it's done. So there's for. I think now it's I can tell you a definition later. It's too long to give a definition now. Okay, so it's basically it's like local is given by a so-called bounded over surfaces. So okay. Then you need to glue them together. Okay. So there's a vibration ciphered structure there. So there is if one uses Thurston previous work, one needs to only the case of this for closed manifold. Because that's because if there's a thin decomposition, we already have incompressible tori, then the Thurston theorem already says there's a hyperbolic structure. So the case for closed three manifold was a weak version of Mann conclusion of Shioda Yamaguchi in a series of papers. So there are some more reference on that, and because this theorem depends on Perelman's another unpublished preprint in the handwritten form. So So it was pointed out by Perelman himself. This hard result can be avoided with actual assumption 3. So actual assumption 3 was not in the Shioya Yamaguchi's work. Okay. It's more like differentiable assumptions. So it's not needed for topological conclusion. But with that, you can avoid this stability theory. So also more recently, there's a related work on by some French mathematicians. So it's on the archive. So there are also shortcut for proving a Poincare conjecture without proving a full geometrization conjecture. So this is which I already gave. It's simply connected, then the empty becomes empty for t sufficiently big. Okay. So this was done by was proved by using a minimum surface again. And you can read the book for more details and description of these things. So maybe I say briefly because time is I have a few more minutes. So say a few minutes. I want to say a bit about the situation in the 4 dimensions. So it's also partly one of motivation. I spent some time reading, understanding this work of Perelman. So in the 3 dimension, Einstein rich curvature does not determine a curvature pointwisely, unlike in the dimension 2 and 3. So for example, the easy case to see the easy way to see that is you look at complex projector space, which is a homogeneous space. It has an Einstein metric because it's homogeneous, but it's not a space form. So it's not like quotient of S4 or R4 or H4 hyperbolic spaces. So what a canonical metric structure on a 4 manifold? So in dimension 4, the structure group is SO4. So this is just a 4 by 4. This is the algebra of rotation orthogonal matrices. So the algebra, which is given by these 4 by 4 schizommetric matrices, is decomposed into 2 copies of 3 by 3 schizommetric matrices. So this is very long. So this decomposition can be given by a Hodge operator, which is a linear operator defined this way on the bivectors. Okay, on the bivectors. So you can you define a basis, then you can extend as a linear operator on the whole bivector space. You can also extend this to a manifold with respect to with a given metric. Okay, so you just do this operator fiberwisely. So this induces a decomposition of a bivector by tangent vectors, tangent bivectors for any given manifold. So with respect to this decomposition, if you look at the curvature tensor, curvature operator, now this time is 4 by 4 matrix. So then you have decomposition into 3 by 3 matrices. So you can write this in terms of so then the curvature has a certain special form. So W here is a decomposing of W plus or minus is called a Weyl tensor. So it has its geometric meaning is it tells you when a metric is conformally flat, namely when the metric is flat after scaling. And Z is a Chestnut's rich curvature. If it's 0, that means your metric is Einstein. Okay, and S is a scalar curvature. I should use R here. Okay. So there are 2 types of canonical metrics on a 4 manifold. It's basically also all similar to called self-dual type because the previous 4 by 4 metric has certain special form. So one is G is Einstein, namely Z is 0. So it's a self-dual this way. Okay. So other ways you can say it's anti-self-dual of constant scalar curvature, namely W plus is 0 and S is 0. So this is very special class of metrics for four manifolds. So in the case of Kähler geometry, there are also extremal metrics. That is Kähler metrics with constant scalar curvature. So in this case, W half is very similar to this. So in this case, the half Yu tensor W plus can be written as a function of S. So instead of 0, but it's determined by a function of S. So it's just some constant. So these are constant metrics. So anti-self-dual basically also in some sense include the Kähler metrics. Can include Kähler metrics. So anti-self-dual things already studied a lot in the geometry of four manifolds. For example, when Donaldson used the anti-self-dual connection to define an invariance and studying a differentiable structure of that. So anti-self-dual things, duality plays a big role already. But here we are more emphasized on the intrinsic structure, on the metric structure. So existence of such a canonical matrix imposes strong topological constraints and the underlying four manifolds. I just give two examples for sake of time. For instance, if you assume M is homotopic to a force field and admits anti-self-dual metric, then it's diffeomorphic to force field. It's not difficult to prove. Okay, it's basically using a certain signature formulas and so on. So for Einstein four manifold, we also have so-called Hitching sort inequalities, and later on is with help of the Separate-Witten equations, you can get more constraints. Okay. So there are also many existence results. So I'm just in 2 minutes. So here are a few existences. There are many existence results of Einstein metrics and also anti-self-dual metrics. But still, there's one question: is the natural way of natural decomposition of giving four manifold, such as each piece either admits a canonical structure as above, or is of if understood topological type. Of course, Hamilton-Ricci flow provides a method in the case of Einstein metrics, but there are some technical difficulties to overcome. Okay, of course, key issue is still to study singularity formations. Okay, so another interesting question is there an analogous deformation process for anti-self-dual metrics? So, namely, you're giving a metric. Is a good way of deforming this metric towards anti-self-dual? Just at the moment, don't even worry about whether one might develop singularity, analyze singularities. That's those technical issues. Just is that formally there's a way approach. So in the last couple of years, joined with Jeff Chigger, we had the program try to understand how Einstein four manifold degenerate or develop singularity. So those are static solution of Ricci flow. It's not Ricci flow yet, but it's the first step towards the Ricci flow. And so we basically get two things, and so curvature bound, namely the curvature is uniformly bounded without outside finite many points, where the Cauchy singularity may form. Okay. So we completely understood where the curvature become unbounded in a sense. Okay. So we also know how when we also proved when the Einstein manifold can collapse. So basically only when these two cases. Okay. So in the case of for example, in the case of Einstein manifold with negative scalar curvature, it cannot collapse because we have low bound on the injectivity radius at many and a sufficient large set of points. So this is a more analytical way, but maybe I just skip it now. So so it also remains to analyze what are possible limiting Einstein spaces. So we need to, in order to finish, we need to this is work in progress, and there are also some results for anti-self-dual metrics, and which is slightly we need more assumption in the results. So this is like in a non-collapse case. Maybe I stop here. And so, thank you.
Você pode ver as 9 horas de conferências de Gang Tian no website da IMPA sobre a conjecture do Poincare. 9 horas dessas conferências que ele faz aqui no mês de julho. Tem perguntas? Are there any questions? Yes?
So that's I guess I skip it. so to study this, you first in 4 dimensions the key estimate you need to bound the curvature. So we can do it now for Einstein matrix. That's a static solution of rich flow. I think this can be extended to rich flow, but not yet.
Okay, merci beaucoup. Thank you very much.